Ladies and gentlemen, good morning. My name is Andrea Zanichelli, and I'd like to present you a paper titled The Fracture and Mechanical Behavior of a Geo-Reinforced Mortar. First of all, I really would like to thank my co-authors from the University of Parma in Italy. The present research work deals with the experimental investigation of the mechanical properties in terms of both flexural and compressive strength and the fracture toughness of mortar specimens reinforced with graphene oxide nanoplates. My presentation consists of the following sections. After a brief introduction related to cement-based materials reinforced with nanomaterials, I will describe the experimental campaign carried out on geo-reinforced mortar specimens. Then, I will focus on the results obtained during such an experimental campaign, and finally, some conclusions will be drawn. As is well known, cement-based materials, that is mortar and concrete, are the most used construction materials all over the world, and this is primarily due to their low production costs and high versatility in response to the design requirements. Despite the several desirable features, the major disadvantages of such materials are attributed to both their low cracking resistance capability, that is to say, a low fracture toughness, and to the presence of intrinsic defects. Therefore, improving the mechanical properties and reducing the size and the number of defects would lead to increase the performance and durability of these materials. An effective way to enhance the mechanical performance of such materials is obtained by adding nanomaterials into the cement-based matrix, and among nanomaterials, graphite or graphene-related materials represent reinforcing bidimensional nanofillers in the form of nanoplates, able to improve the macroscopic properties of cementitious materials due to their excellent physical and chemical properties. Moreover, according to the technical literature, GO nanoplates can regulate the microstructure of hydration crystals during the cement hydration reaction, leading to an increase of the mechanical strength and fracture toughness of GO-reinforced cementitious composites. In such a context, the goal of the present paper is to investigate the flexural and compressive strength and the fracture toughness of a cement-based material reinforced with the 0.03% in weight of GO nanoplates. Now, first of all, I would like to describe to you the experimental campaign carried out at the testing laboratory of the University of Parma. The raw materials employed for the preparation of mortar specimens were Portland cement, standard sand, polycarboxylate superplasticizer, and graphite powder. Then the GO in aqueous solution was obtained from the oxidation of graphite powder, which were carried out by means of the Brody method. According to the UNI EN 196 recommendation, the mixture proportions here reported by weight were adopted. Moreover, note that plain mortar specimens were also prepared as reference. So, the flash slurry was placed in prismatic molds and compacted by means of a vibrating table. Then the specimens were cured in laboratory for 24 hours under standard climatic conditions, and after the molding, they were submerged in water at room temperature for 28 days. Then, the flexural strength, the compressive strength, and the fracture toughness of both plain and GO-reinforced mortar specimens were experimentally investigated after 28 days of curing. Firstly, 3 prismatic specimens with the nominal geometrical sizes reported here have been subjected to 3-point bending tests in order to determine the flexural strength. The tests were carried out under load control, and each specimen was monotonically loaded up to failure. The flexural strength, Rf, has been computed as a function of the experimental value of the peak load, Pf, according to the present equation. Subsequently, the 6 halves prismatic specimens resulting after performing the flexural tests have been subjected to compression tests in order to determine the compressive strength. The tests were carried out under load control until specimen failure. By employing the experimental value of the peak load, Pc, the compressive strength, Rc, has been computed according to the equation reported here. Moreover, 5 prismatic specimens with the nominal geometrical sizes reported here and with a notch in the lower part of the middle cross-section have been subjected to 3-point bending tests in order to determine both the elastic modulus and the fracture toughness by means of the modified 2-parameter model. Such a model, proposed in the past by Vantadori and co-workers, allows us to take into account the possible crack deflection occurring during the stable crack propagation, even in the presence of a pure mode 1 remote loading. According to such a model, during the test, the specimen is monotonically loaded under crack mouth opening displacement control up to the peak load, as is shown in the figure on the bottom right side of the present slide. When such a load is achieved, the post-peak stage follows, and then, when the force is equal to about 95% of the peak load, the specimen is fully unloaded in order to find the unloading compliance. Finally, the specimen is reloaded up to failure. So the elastic modulus and the fracture toughness have been computed as a function of the experimental values of both the peak load and the initial and unloading linear elastic compliances. In the present slide, the results obtained from both flexural and compression tests are summarized. The mean value and the standard deviation of the peak loads Pf and Pc and the flexural and compressive strength Rf and Rc are listed in the present tables for each specimen type. In particular, it can be highlighted that only a modest increment, that is about 4% and 3% in terms of flexural and compressive strength respectively, is achieved when GO nanosheets are added to the cement-based composite. Moreover, such differences may be more related to the aleatory variability and measurement errors than to the effectiveness of GO addition. Regarding the fracture tests, the experimental load crack mouth opening displacement curves are shown here for only one specimen of each type being examined for sake of clearness. Moreover, the mean value and the standard deviation of the peak load Pmax, the elastic modulus E, and the fracture toughness K are listed in the present tables for each specimen type. A significant increase of the peak load can be noticed for GO-reinforced specimens in comparison to PM ones, whereas the elastic modulus is almost constant. Moreover, the best performance in terms of fracture toughness is observed when GO nanoplates are used as reinforcement materials, with an increase of fracture toughness mean value of about 26% with respect to PM specimens. And now let us move to the conclusions. So in the present research work, both the mechanical and the fracture behaviors of a cement-based material reinforced with GO nanoplates have been experimentally investigated. In particular, 3-point bending tests on both unnotched and notched prismatic specimens, as well as compression tests, have been carried out in order to determine the flexural and the compressive strength and the fracture toughness of both plain mortar and GO-reinforced mortar. On the basis of the experimental results, it can be concluded that the addition of GO nanoplates is able to slightly improve the mechanical properties of the present cement-based material and to significantly increase the mortar resistance to fracture in agreement with the results reported in the recent technical literature. Different percentages of GO reinforcement should be now investigated, as well as the influence of GO addition on the hydration process at different curing times. Thank you for your kind attention.